Thanks for coming. I'd like to welcome you to the Center for Polar Studies lecture. We're privileged to have Dr. Kathy Licht from Indiana University-Purdue University in Indianapolis with us tonight. I've known Kathy for a while. We've worked out a few Antarctic camps together and had some good times. Her husband is also a colleague of mine. He's a mountaineer, spent 28 odd seasons in Antarctica. He's been a mountaineer for me a number of times. He's here as well, so I thought I'd introduce Peter, even though he's not going to talk. But anyway, Kathy got a BA at St. Norbert's College, much like this college. In fact, the chairman of the department at St. Norbert's College right now is a graduate of Augustana, Nelson Hammond. She got a master's at the University of Colorado Boulder and a PhD at the University of Colorado Boulder. And she has been doing research in Antarctica for a while. She's spent 6 seasons down there doing research. She's got a couple more to catch up with me, but she's a hell of a lot younger than I am, so I think that's probably going to happen. And we're hoping a year from the fall to be down there again together. Unfortunately, I don't think I'll get Peter as my mountaineer because I think he's going to be her mountaineer. But he's promised me he'll find someone good. Anyway, thanks, Kathy. I'd like to introduce Kathy Licht. And the title of her talk is The Secret of the Antarctic Sand, Tales from the World's Largest Ice Sheet. Yeah.
Stay awake? Okay. Well, thank you so much for having me here. I have enjoyed my visit so far talking with some of the students. And what I wanted to mention before I get into the science, as Bill pointed out, is that, I did my undergraduate at a small liberal arts college, and you never know where it might take you. So this was the field season where we overlapped with Bill. And that's me on the left, and the guy in the middle was my undergraduate geology professor. So I was going into the field, and I said, hey, I need somebody who I know is going to be a great field assistant. So I called up my professor and said, hey, Tim, what you doing? How about going to Antarctica? And so he couldn't resist, so he came. And then I had a student all lined up to go, but she couldn't pass the medical, so at the last minute I also needed a student. So I said, hey, do you have anybody at St. Norbert who I could take with me? So Nicole on the right, who some of you now know as Pinky, she ended up coming down as an undergraduate and then coming and doing a master's with me. So it was fun to have sort of 3 seasons of St. Norbert folks down on the ice. So before I go any further, I just want to put up a list of lots and lots of people who have helped out. On the left are all of the students who've been helping me out as of late, a mix of graduates and undergraduates. And to do research in Antarctica takes a whole lot of people. So I haven't listed, 90% of them, but the field teams are really important. So life in Antarctica can be a little bit trying at times and also a blast. So it's important we pick critical field teams and have mountaineers with us to keep us from hurting ourselves. We also have pilots who do some amazing things. So I want to mention crazy Jim Happy. He is crazy, but he can put an airplane nearly anywhere, and I'll show you one of the spots. I still can't believe he put a plane there. And he's still alive, so he's clearly a great pilot. So this work has all been funded by the U.S. National Science Foundation. So this is a liberal arts college, so I thought I would bring in, a little poetry. So when William Blake first penned the line, "To see the world in a grain of sand," I don't think this is what he had in mind. But sometimes geologists have to go to extraordinary measures to get our samples. So in this particular case, we are trying to flatten out this really rocky moraine surface so a helicopter could come and pick us up, and all of the samples we had collected. So why sand? Why am I talking about sand? Surely some of you who are in the upper level part of the geology major have thought a lot about sand. Maybe some others of you who are new have not. So as a geologist, I think about sand as really a time capsule of Earth history. And we can learn a lot of things just from looking at some handfuls of sand. For instance, on the picture on the left, those little pink bits are fossils. So if they're marine sediments or lake sediments, things on the beach, you might find fossil parts that can tell you something about what was living in that environment. The one on the bottom left is some Hawaiian sand, black sand from the big island of Hawaii. And that composition can't be found everywhere, right? So if you go to Lake Michigan, you're not going to find black sand unless maybe you're out a place you shouldn't be. The age is also really valuable. So I'm going to talk a lot more about the age, so I'm going to skip over that one. But also the shape. For those of you who've had your set strat kind of classes, you know that rounding of grains tells you something about its history. So we can put together all of this information to try to learn something about Earth history just from these little sand grains. So where does sand come from? This is a picture I took from Wharengi, which is in New Zealand. And it's a great example of, here's a big block of sedimentary rock. So you have a lithified rock, you're breaking it down by wave action and depositing it right on the beach. So that's a short story for sand. You start in a rock, you move 100 meters, and you end up on the beach. But of course, not all sand has that short of or easy of life. So if we think about here in the US, now we're looking at the Mississippi Delta here. And so the Mississippi is sort of snaking down back here. And you might think about the sand that you would find down in this area. So it might have started in the Paleozoic, been eroded from some terrain, been transported and deposited, say, in the Michigan Basin. And then sometime much later, it was eroded, transported, deposited. In this case, you have it buried, lithified, uplifted, and then you can start the process all over again. So a single sand grain can go through a very complex history. So it's easier to interpret the one that was just eroded and deposited nearby, and the ones in glacial terrains in particular are much more complicated. So we can have deposits that were sand grains eroded from Canada, brought down through the Great Lakes into the Midwest, and then eventually taken down to the Mississippi by lots of different mechanisms. So when you find that grain of sand, the clue is, can you figure out how it got where it is and what that means? In Antarctica, it's a little bit harder and a little bit easier. The easy part is you can't see anything, so it's really up to you and your imagination to put the story together. So I'm going to talk about a variety of sands from Antarctica. The first sand you encounter when you arrive is what happens at McMurdo. McMurdo is the main U.S. base of operations. There are over 1,000 people there in the summertime, so it's like a small town. Anybody from a small town? Okay, what's in every small town besides a Walmart? A church? There is a church? Bars, okay, that's all we need, right? So all of those things are in McMurdo, but there's also a lot of dust when all the snow melts. So you could be walking down the street and if the fire trucks go by, you just get covered in a whole lot of dust. When it's really windy, that can be sand. The more natural sand is in the Transantarctic Mountains. The rocks you see in front of you here is part of this beacon supergroup, and there's lots and lots of sandstone. It makes for beautiful scenery. Interestingly, there are also sand dunes. These are in the dry valleys, and you see folks here surveying what look like, normal sand dunes, but they happen to be in Antarctica. They don't occur in many places because there aren't that many ice-free places. But this reminds us that Antarctica is a desert. It's the world's largest desert, and you can get snow dunes, and you can get sand dunes. The ones I want to focus on tonight are sands that are contained in glacial deposits. So here's a big outlet glacier coming off the polar plateau out towards the coast, and along the way it has eroded these rocks that are sticking up and transported that debris, and it's now sitting at the surface as a pile of till. So we know in the Midwest we've got till all over the place. This is sort of bit of a different way to think about till. Okay. So if you were to walk across the surface, one, it would be pretty treacherous. You'd have about this much till. It's usually pretty thin, and rocks. It's sort of like walking on ball bearings with ski boots on. So not that much fun sometimes. So what's under all of this is ice. So there's ice under all of these till deposits that I'm going to talk about. So why do we care about this sand that's in these glacial deposits in Antarctica? Well, we're looking at it. You can look at it for a lot of reasons, but for us it tells us the history of Antarctica's ice sheets long after they're gone. I'm going to start up this animation. This is a model that was run by a guy called Nick Gollage, and what you see here is the ice sheet during the last ice age, and the color here is speed. So you see that most of these dark blue colors are very slow ice in the interior, but the ice is channeled out into faster flowing ice streams in certain places. So if you follow the colors, they sort of shift back and forth over time, and then once the ice sheet starts to retreat, you'll see a major change in this configuration. You stopped at 22,500 years. I guess that's the last glacial maximum. We're going to stay there for a while. Let's see if I can. I'm going to run through it quickly, I guess. Okay. So these ice streams, or these regions of fast-flowing ice, are things I'm going to come back to a little bit more. We don't really understand a lot about what causes them to form. You could walk from here across here. There'd be no mountains in the way to channel the ice, but those ice streams are flowing 2 orders of magnitude faster than all of the ice around it. Okay. If we can get past 22,500. No, okay. We're going to stay there. Imagine, if you will, this ice retreats and the ice sheet shrinks in size. Okay? So it shrinks back to the configuration of today. So we know the ice sheet was this big from the geologic evidence. The models can reconstruct that. But can we figure out where this fast-flowing ice was, what direction the ice came from? Okay? And the history of that is in the sand. For those of you new to glacial geology, we think of ice sheets as giant conveyor belts. So there's a little cartoon at the top, which is not really like glaciers because the debris is coming out on the surface and constantly moving forward. For glaciers, in some cases rocks can fall off the mountains onto the ice surface, but a lot of the debris is transported along the bed. So as the ice is always flowing forward, it's constantly acting like a conveyor belt and bringing debris forward through time. So at the glacial maximum, when the ice advanced, it's bringing debris from somewhere upstream. We don't know exactly how far it's been transported, but it's transporting this ice and debris quite a long distance in some cases. And why does all of this talk about the Antarctic ice sheet matter? There's lots and lots of reasons, and you might talk about these in some of your other classes, but the ice is really important in a global sense. So yes, we are interested in this place at the bottom of the planet. It's an amazing place to go to. It's incredibly beautiful. But in a bigger sense, it's important globally. So I put here this bathtub, and this blue line here represents sea level for the ocean during the last ice age. So sea level was lower, and as the ice melted, as the Earth warmed up, the northern hemisphere ice sheets disappeared, sea level rose, and so global sea level rose on the order of about 400 feet. Okay? So that dramatically shaped our coastlines. What's happening today? That's a good question. In the next century, we expect that the rate of sea level rise will increase. It seems to have doubled within the last century. We don't know if it's going to double again, but the best estimates for the next century are a sea level rise of 0.85 to 2.7 feet. So, here, do you have to worry about it? Yeah, not so much. But if you're New Orleans and you're already below sea level, you got a problem, right? So at least 10% of the world's population lives within 10 meters of sea level. So 10%, how many people live on the planet? A few billion? That's a lot of people. So there are a lot of geopolitical, economic issues that come with sea level changes. And so suggest many coastal cities eventually to be abandoned with the Antarctic ice collapse. So there were several studies where people modeled what happens to the ice sheets, and a couple of people said, look, it's past the point of no return. Part of the West Antarctic ice sheet is going to go, probably in the next couple of 100 years. It could be as long as 1,000, but we don't think it's going to take that long. So if you take that segment of the ice sheet out, you can raise sea level up a lot more than 3 feet. Okay? So that's why people are very interested in this particular topic. The temperature trends in Antarctica are a little bit mixed. On the Antarctic Peninsula, this area circled here, you see all these red colors, and this is the amount of temperature increase per decade. And so what to take home from this is that this part of Antarctica is warming, and it turns out, unfortunately, this part of the ice sheet seems to be particularly sensitive, right? So you can heat from the atmosphere, but ocean heating from underneath floating ice can basically attack the ice from both directions. And this area here is where all these studies were about that came out in May, and this is sort of the scary place that people are really watching. The peninsula has some fairly long-term records of climate for Antarctic standards. So it's warmed 3 degrees Celsius in 50 years. So this is much higher than the global average. Now, it's not the same everywhere. So East Antarctica, which is this half here, you see a mix of light golds and blues. So it's a little bit cooling, a little bit warming, but not too much. This area is really big, and it's hard to study, and we don't have much data from it. So there's some variability in the scientific community on how much is it warming, how much is it cooling. This, I would say, is a work in progress, but this we know quite well that warming is happening here. Okay, so that's one area we're concerned about. The study of the area I'm going to talk about today is this part, and it's the ice that feeds into it starts sort of in the zone, the scary zone where there's lots of warming. So that's part of the reason we're studying this particular spot. So here are just a few fun facts about Antarctica, if it's not a place you think about a lot. First of all, it's really big. So if you take the US and you stick it inside East Antarctica, and now it's turned sideways a little bit, it's like driving from Maine to California and seeing nothing but flat white, except a few peaks as you cross the Rocky Mountains. Can you imagine sitting in the car, seeing nothing but flat white for days of driving? Okay, so that's what most of East Antarctica looks like. There is a big mountain range that cuts through it. These are the Transantarctic Mountains. And so again, if you can imagine the Rocky Mountains all filled up, covered with ice, except the highest few peaks, that would be like the Transantarctic Mountains. West Antarctica is quite different. There's a big segment here that's below sea level. So this is an old rift basin, and so it's quite deep below sea level. And then there would be an archipelago of islands along this particular side. So this holds 90% of the fresh water on the Earth's surface. If it all melted, the whole thing, you could get about 200 feet of sea level rise. Yep, so southern Indiana would be, just about beachfront property. So it would flood up the Mississippi, so by now, you guys are young, right? Oceanfront property. The average ice thickness is over a mile, okay? The thickest ice is over 15,600 feet thick. That's a lot of ice up over your head. And some of it's really old. So people have drilled cores in different places through the ice sheet, and we are pretty confident that some of the ice is about 1 million years old. Okay, so that's what you can recover right now. The ice sheet has been around in this configuration for much longer, but the ice that we have a climate record of is sitting there that's 1 million years old. That's pretty cool. So we've got today's ice sheet. If you look at it, most maps show it as white. You're like, okay, it's a white ice sheet. It's flat. What's really going on there? So people do these really cool things. They take all the satellite imagery they can get, and they make maps of how fast the ice is flowing. So this map shows it a different way. This is the speed of the ice flow. So these areas in blue colors here are outlet glaciers that are flowing fast. So you can think there are mountains between them, and the ice is squeezed through those and you jump across this boundary, the ice is flowing 100 times faster. That's pretty crazy. Peter's worked in this area, and the ice is really stretched and crevassed and scary as all heck. If you want stories, talk to him. The ice streams, because they drain a lot of ice out of the interior, they affect the ice sheet stability. If you have a way to pull the plug and drain a lot of ice, you can cause a lot more sea level rise. So people are interested in these for their stability. So it's essential to get these right in the reconstructions, right? So we want to make sure we get those. How do you find them? That's an interesting challenge. What we see today is they're here in this place, again, where there's no mountains interrupting them. Here's a funny view from out in the ocean looking up at the Transantarctic Mountains. And the dinosaur site is up about here, Mount Kirkpatrick, roughly in that area. So these are tall mountains, and this area we're talking about is in this low-lying ice. So we want to figure out how big did these things get during the Ice Age, and there's no ice left, so we use the sand to help us. So this is significant for a lot of reasons. It helps us get the dynamics right in the models. Okay? So by dynamics, I mean these areas of fast-flowing ice, these ice streams. If you miss that in the model, you miss a lot of important predictions for how ice sheets respond to climate change and how they'll impact the globe. So we need to reconstruct the past ice sheets, and that helps us figure out rates of change. How fast does this thing change? Can it collapse in 200 years, as these papers were saying? Do we see any geologic evidence of that? In order to look for it, we have to know what the ice sheet looked like in the past. So here's what models look like. So you see a lot of funny blue lines, right? So Some areas are quite extensive. So now the main glacier is flowing out this way, and this is all debris draped on top of the ice. And you can see the airplane wing here, we're flying over it. This happens to be the southernmost outcrop in the world, so there's nothing between here and the South Pole. It's about 180 miles from the South Pole. Now, to get samples from the middle of here takes a little while. There are people here. I don't know if you can see those. So this was the worst hiking I've ever done. You guys were talking about some kind of crazy hiking in the Grand Canyon. This was just nutso because this is the ball bearing with ski boots, and then you add a 40 or 50 pound pack and a coat that comes down to your knees. And you know, it's a little tricky. So Pinky, undergraduate with me, she ended up just walking with knee pads on because she fell down all the time. But you know, we got good sand. The question is, how do you sample all of this stuff that's buried by the ice, right? There must be a place where you can gather this debris without drilling through the ice sheet. So I'm going to take you to this spot here. And again, the color is velocity. And this is Berg Glacier. So this is the crazy gym site is sitting right on here. But that material turns out to reflect the local wall rock. So the rocks were breaking off, falling down, or being transported short distances. But here's 1 million square kilometers, and I want to know what's under here. So how are we going to do this? So we thought for a while, we scratched our heads, and we went to the literature and did a little research. We said, well, way up at the top of these, you find these little rocks poking out. These are the tops of mountains. They're called nunataks, and there's nothing else upstream. So if we could find deposits plastered along these, maybe they're telling us that everything that's been scraped from the interior and somehow brought to this spot. Why would that work? That's what the proposal reviewers said. I'm like, we're not so sure this is going to go. But we said, Mother Nature might do the trick for us. And we took a page from the playbook of the meteorite hunters. How does that work? Okay, so this is a cartoon from Willens and Cassidy, and they show meteorites coming in and landing on the ice sheet surface. As the snow falls, they get buried over time. And that because the ice is always flowing, it actually carries them toward the coast. So these lines show a meteorite that's been buried and is being slowly transported toward the coast. But in this case, it runs into the mountains. So what happens? So as the ice runs into it, it actually turns upward. And Antarctica is a desert. Remember I said it's so dry and so cold that the ice just sublimates away. So now you've got these meteorites scattered in the ice. You just keep taking the ice away and you're left with a pile of meteorites. So they found over 20,000 meteorites in Antarctica this way. Like, well, if they can do it, maybe we can use that to our advantage. So we went to some of these sites, and lo and behold, we found rocks that look like this. You may have seen these in this area. Striations, facets. This is the key sign that it was transported at the base of the ice sheet. It came from down here, was scraped along the bottom, and brought up to the surface. Now these are just like taking a core all the way through the ice sheet, but they've been scraped from a pretty broad area and integrated and brought right up to the surface. Like, thank you, Mother Nature. Okay? So now we have the local debris, and we have this material from the interior. So this is what we ended up with. All of these red dots are our sample locations. There are 39. We hope to get 40. So in Antarctica, that's ridiculously good. Right? When I went to McMurdo, I put this map up and said, this is what we plan to do. And there was a mix of laughter, because there were a lot of experienced people in the room, and gasps, like there's no way you're going to get that. So we're fantastically lucky to get this data set. So we're going to compare those to what's under the ice streams, and then those materials that were collected that are older from the last glacial maximum that were collected on the seafloor. So what we do in the field is really simple, right? We go out, we're cold. So this is poor Pinky on quite a cold day at Mount Howe. And what we do is we lay out a rope that's a square meter. And for this particular study, we picked up every single pebble because we wanted to know it was in the bigger size fraction, because that helps us understand what's in the sand size. And then we simply took a couple big scoops of till and put it in a Ziploc bag and brought it home. So what we did in the field was pretty simple, which is okay when it's really cold. Sometimes it's a little hard to concentrate. sampling scheme. That's what we did. And one question we had is, okay, we're sampling all these deposits on the ice surface. How old are they? Right? So this is for the geomorph class. Okay. I know your questions. Right? So we did a transect of the debris across this big moraine. Now, here the ice is flowing in this direction. And this is bedrock back here. And so you can think of this as a big cul-de-sac. And the debris is just being pushed back into the cul-de-sac. Okay? It's a little bit like an eddy at the edge of the glacier. So this is all debris sitting on top of ice. And so we collected sand samples from this transect. We also dated them at the surface. And we know that at this edge, all of the samples have been on the surface for less than 10,000 years. As we go back, these have been on the surface, so exposed to the light for 10 to 20,000, 20 to 60,000, and the ones back here are at least 200,000 years old. So we have almost a continuous recorder of how the sand composition changed through time over at least 200,000 years. It may even be 500,000. So our proposal for this coming season, or for the next project, is to come back here and figure out how these things actually form, because we don't know. So how do you figure out how long these things have been exposed at the surface? You ask them? You ask their mother? No. We used cosmogenic nuclide dating, and this was mostly done by my colleague Mike Kaplan, and I call this the suntan meter, right? So here's the way it works. There are rocks sitting exposed, so as a glacier retreats, it leaves rocks behind, and cosmic rays from supernova explosions in the past, cosmic rays are always hitting the Earth's surface. They're hitting us now. Right? What these do is interact with minerals, in particular quartz, and it causes the neutron bombardment, causes changes, and it causes transformations to produce cosmogenic nuclides. There are beryllium, aluminum, chlorine, helium. There are a whole variety of cosmogenic nuclides. And the key is that over time, the nuclides increase. So if you're measuring beryllium-26, or beryllium-10, sorry, or aluminum-26, the more of those compounds you find in the rock sample, the longer they've been exposed. So that's pretty easy. Right? So their sampling method, it looks like they're beating each other. They're really not. So they just take off flakes of the rock. So they find big boulders they don't think have overturned, and they simply just beat the heck out of it with a hammer because they're sampling really flat, solid surfaces, so it takes them a long time. So they whale away on it, and of course the chip that comes off goes flying into the moraine, and you can't find it, so then they whale on it again. That's their sampling process. The preparation of the sample takes a long time and is full of really scary chemicals like hydrofluoric acid, but it allows them to measure these cosmogenic nuclides and figure out how long the rocks have been exposed on the surface. So, now, back to sand as a tracer. We're not going to use fossils in this case. We've used composition, so we've looked at all the kinds of sand grains, but I'm not going to talk about that. We're not going to talk about shape, but we're going to focus on age. So what age are we talking about? So 3 kinds. There's a crystallization age. So if these are all quartz grains, let's say, when did that quartz go from being a liquid in a melt deep in the earth to being a solid piece of quartz? That's the crystallization age. Then you can take that piece of quartz and you can erode it out of the granite and put it into a sandstone. That's the deposition age. And then the exposure age is the one I just showed you. How long has it been exposed to the sunlight? So I'm going to focus now on the crystallization age because that can be a really great tracer of ice. How does this work? We're not going to use quartz in this case, we're going to use zircon. So zircon is a silicate mineral, and if you wonder, you're like, yeah, zircon must be weird and rare. Their whole volume is written on zircon, so it's a very useful mineral. It forms in igneous rocks, particularly granites. Erosion transport process several times. The important thing is it's resistant to heat, and so you can bury it in the earth, 10 kilometers, it still retains its original crystallization temperature. So that's pretty cool. And you can weather it, you can do whatever you want to it, and it's still zircon. It's kind of like quartz in how stable it is. And as an aside, it's used in high temperature industrial products, ceramics, and it's actually also used as a gemstone. they grow, right, as they get bigger, and they get these nice euhedral shapes if you're lucky. Sometimes they're pretty rounded if the grains have been through several sedimentary cycles. And once we zap it with the laser, we blast a hole in it, and that gives us the crystallization age of that particular grain. So we do one sand grain at a time. So we measure 100 grains per sample if we can, and we're trying to make a geographic fingerprint. Okay? Let me explain to you how that fingerprint works. We call this following the breadcrumbs. So let's say the rocks over here are 100 million years old, the rocks here are 530 million, and the rocks here are a mix of ages. Okay? So if you find a granite, an igneous rock in that area, that's the age you find. So if the ice erodes that and transports it, you can actually follow that piece that started from a granite that was eroded by the ice sheet and transported all the way out here onto the seafloor, and you can trace them back to their source. So you might get an answer that looks like this, you might get an answer that looks like that, but it allows you to figure out how much ice came from different parts of the ice sheet. Easy, no problem, right? Except, you know, the terrains look more like this. It's much more complicated, and we don't know half of them because they're covered by ice. So it's a little bit trickier to try to trace these flow paths when we know so little about the geology. So we measured over 5,000 grains from all of those samples I talked about, and fortunately, we found one really good tracer of the ice streams. So I don't want to show you all of the data, but I'll tell you that here are our ice stream samples, and here are all our samples from the Transantarctic Mountains. And what we found is that there's a distinct age of 100 million years in the sand grains from these two ice streams, right? So for the thousands of grains we measured over here, we didn't find one grain that was 100 million years old. Like, oh, thank goodness. So then when we looked out here in these deposits from the last ice age, only these cores from these areas had the 100 million year grains as well. And that makes sense, right? They're closest to this area, so it let us draw flow lines and figure out which way the ice flowed during the last ice age, and try to get back to that question of where were their ice streams? Did they get really big? People originally thought these ice streams came all the way around and ran way over here, and we can say, that didn't happen. So now we have good constraints on the model. Okay? So we're really just tracing the grains of sand. So now we can check models versus reality. So here's another one of those models where these blue lines are what the modelers make, and they actually took our data and they overlaid it on top of theirs and said, how do we do? So the red lines are our data, and you can see in some cases they're pretty close, some they're less good, and so now they can change the models. They can say, well, maybe I got too much ice coming out of here, so I can dial that down and try to get their model as close as they can. Once they do a pretty good job with matching the geologic data, then they project forward. Like, you want to know what's the ice sheet going to do in the future, right? How much is sea level going to rise in the lifetime of my grandchild, right? So you ask the modelers, they're the ones who can make the best predictions. So this is where our data really fits into the puzzle. So in the end, what we found, this is Pinky, that sand is a really, really useful thing to trace ice sheets of the past, right? We're still learning how to do it. There's lots of different kinds of tricks we can use. There are lots of different tracers that people are just starting to try, but it helps us learn a lot about ice sheets of the past. We also have a little bit of fun while we're doing it. This is from this last season. It's the pilots. You never know when you need a foosball table in the middle of the ice sheet. They got riding a snowmobile too, but that's another story. You also find interesting things. This is, in the middle of a moraine that's 6 kilometers long, and you find a bench for lunch. Okay? So in the end, we really think of geology as a 4-dimensional challenge, right? So we're thinking in 3D plus time. And so for those of you new to geology, I encourage you